All right, welcome to Introduction to Ecology Lesson 5. Today we're going to be talking about the physical environment, the determinants of the physical environment, and why that matters to different organisms and to ecological systems. So when I talk about the physical environment, I typically am thinking about two broad categories. One is climate and the other is the chemical environment. So within climate, the main features are temperature, wind, and precipitation. And you can actually see that map of different climate types across the United States. So for instance, you see the southeast is all pretty much one climate type, except perhaps that little area running down along the border of Tennessee and North Carolina, where you actually have a different climate type, and that's of course the Southern Appalachian Mountains. But then as you move towards the north, towards Canada, where I'm from, you see right along the Canadian border, you get a very different climate type. And then out west, there's a ton of various climate types because you have a lot of mountains, deserts, coastal areas with even temperate rainforests. And so you get a lot of variation, and all of those different climates have slightly different temperature regimes, wind patterns, and precipitation. So within chemical environment, there's a lot of different things that matter. The ones that we'll focus on, the big ones, are salinity, or how salty either the soil or an aquatic system is. Acidity, which is the pH of, again, either soils or aquatic systems, lakes, rivers, oceans. And then finally, gases, which are typically associated with the atmosphere, but also with aquatic systems where you have dissolved gases. So first we're going to look at climate, and before we do that, I want to make a very strong distinction between climate and weather. Weather describes the conditions that we experience from one day to the next. So that graph on the left-hand side is actually a graph of weather in Clemson in 2017. And so the red line is the high temperature and the blue line is the low temperature on each day in 2017. And there's only one measurement for each day for the high and the low temperatures, because there's only 1 year to make the measurement. So again, that's weather. And what you'll notice is that it's really very noisy. Some day we might be really, really cold, and then the next day it's a lot warmer. Or maybe we have a really, really hot snap, and then it suddenly drops to being very cold. So those lines are kind of going bouncing back and forth all over the place, and that's weather. Climate, on the other hand, is a description of weather averages and variation over many, many years. So on the right-hand side, you see a graph that represents elements of the climate of Clemson, South Carolina. And what you'll notice, it's a lot smoother than weather. And so rather than just looking at the high and low temperatures in 1 year, the red and blue curves that you see in the climate graph are actually the temperatures at that particular day for averaged over many, many years. And so you get that smoothing out of the noise. So rather than just looking at the weather on January 1st in 2017, we're going to look at the weather on January 1st from 1990 through to 2020, or even sometimes a longer period. And again, that's what gives you climate. So climate is averages over many years rather than just a single day, which is what you have from the weather. All right, so why does climate matter? Climate matters because it actually is one of the main factors controlling where species live. And I think this is a really good example. This is a paper from 2017 where scientists tried to use climate variables to predict where particular Australian plants might be found. And the variables that they didn't use all climate variables. They used mean annual temperature, they used the maximum temperature of the warmest month, they used the total annual precipitation, they used the precipitation of the warmest quarter of the year, and they also used the precipitation of the coldest quarter of the year. And with just those 5 variables, they tried to predict where eucalyptus would grow and where another plant, Leptospermum, would grow. And what you'll notice, the maps on the left, the white and black maps, show where the plants are actually found. The black dots are where all the plants are found. And then the colored maps on the right show where the scientists predicted the plants would be found just based on those climate variables. And what you'll see is there's quite a good degree of overlap, because on the colored maps, red is where the scientists would expect to find the plants based on climate, and blue is where they wouldn't, and they're doing quite well at locating where those plants actually occur. What you might have noticed on the last slide is that the scientists didn't just use the average temperature over the year to predict where the plants might be found. And that's because extremes can be more important than averages. So the scientists in building that particular model for Australian plants actually incorporated the maximum temperature in the warmest month. And that's because these extreme climatic events are important in that they often cause mortality. And then that mortality leads to boundaries in geographic distributions or in where those species can be found. Extreme events like extreme high temperatures, extreme low temperatures can also alter population dynamics, and again, that influences where organisms can be found. So not only do you want to look at the average temperature over a year, you also want to look at how high can you get in that area and how low can you get. What's the spread? What are the highest highs and the lowest lows over a number of years? And that tells you sort of more information about who can live in that particular area. A really good example is with tent caterpillars in Canada. So scientists were studying tent caterpillars. They tend to monitor them because they're an outbreaking pest species. And so they undergo these cyclic boom-bust periods, and they're defoliators, so generally they're unappealing. So they're monitored constantly in Canada, and what scientists found is that the population suddenly dropped in going from 1993, 94, 95 to 1996. Now, I said that these were boom-bust kind of populations, but there was no good reason why the population should have dropped in 1996. They tend to go up and down in cycles, and this wasn't the time in the cycle where the population should have crashed. So scientists wondered what had happened, and they actually went and looked in, and what they saw is that in that 1995 to 1996 period, there were a few days in early January where you had the temperature drop to a low below minus 45 degrees. And scientists know that this tends to cause tent caterpillars to die off rapidly. And so it wasn't so much that the whole of January in 1996 was cold, it was that there was one or two nights where it got just too cold for the caterpillars to tolerate, and so they died. So again, this is a case where the caterpillar range might be impacted, and maybe the caterpillar can't grow anywhere where you reliably get 1 or 2 days below minus 45. As long as you don't reliably get that, the population might be able to persist, but in any region where you get that cold snap at least several years out of a period of time, then the caterpillars won't be found there. So again, averages matter, but average variability also matters. It matters whether you get wide swings in temperature, wide swings of precipitation in a particular region. All right. So climate determines where species can live, and that includes average temperature, average precipitation, average winds, and also extreme events. But the other thing that matters is timing. And when I speak about timing, what I actually mean is seasonality. You can have two regions with very similar temperatures, very similar precipitations, but if those occur at different times in the year, you might have very different vegetation. I think a good example is the contrast between Mediterranean environments and grassland environments, or Mediterranean ecosystems and grassland ecosystems. So in Mediterranean ecosystems, that's the picture on the left, and what you'll notice is that it's very scrubby. There's a lot of bare rock, it looks kind of deserty, versus the grassland on the right where you got a lot of growth. Grasslands can be very fertile, that's where agriculture occurs. And even though both of these areas tend to get very similar precipitation, the difference is that the Mediterranean ecosystem gets all that rain in the winter months when it's cold. So the rain tends to occur in January, February, even December. And what that means is it's not really as available to the plants because it's too cold for the plants to grow. So they're not really making use of the rain during that period. By the time we get to the warmer months, March, April, May, June, it's dry already in the Mediterranean environment. And so you just don't have that opportunity for growth. Contrast that with the grasslands where most of the precipitation falls in July, August, September. That's the height of the growing season. And so the rain is coincident with those warm temperatures, and that really allows the plants to grow a lot better. You get a lot more sort of diversity in there. All right, so again, even though you have equal amounts of rain, the fact that that rain occurs at different times of the year, it can actually favor different vegetations and different ecosystems in different places. So once again, we have that Mediterranean ecosystem when we have the rain in the winter, and we have that grassland ecosystem when we have the same amount of rain but occurring in the summer. So that's a little bit about why climate matters to species and the ways in which climate matters to where organisms are found. You might now wonder, well, what determines climate in the first place? Climate is actually determined by, ultimately, the energy that we get from the sun. And so we're going to look at a little bit at the global energy balance, where all that energy coming in from the sun ends up. So overall, we tend to get, averaged across the whole surface of the globe, 342 watts per meter squared of solar energy each year. So if that's 100% of the sun's energy that ends up sort of coming close to the Earth, about 19% of it ends up absorbed by the atmosphere. 49% of that energy, 49% of the 342 watts per meter squared, is absorbed by the Earth's surface. So almost half of the energy that's coming in from the sun ends up being absorbed by the Earth's surface. And that includes the oceans, these sort of land masses, all the plants that are on the land masses, everything that's on the Earth's surface. Another 23% of that solar radiation ends up reflected by the atmosphere and clouds and aerosols and heading back off into space. And then 9% may make it through the atmosphere, hits the Earth's surface, but then gets reflected by the surface. And so again, heads out. So you notice about 1/3 of the solar energy is reflected, and the other 2/3 are absorbed. So those are your energy gains. Now we're going to look at energy losses. And I want to be a little careful here. You're going to see that the total losses end up more than 100%, but what we're looking at is the percent of that 342 watts per meter squared. So the first source of loss is sensible heat, and this is heat that gets transferred through conduction and convection through the atmosphere. So as the winds blow over the Earth's surface, they take heat with them, and that heat gets removed from the Earth's surface, and that's what we call sensible heat. So about 7% of 342 watts per meter squared is lost through sensible heat. We also have heat loss through latent heat, and this is what occurs when you have evapotranspiration. So you probably learned in chemistry class that when you have changes in state, that takes energy. When I turn liquid water into gaseous water, that takes energy, and that energy is what we call latent heat, and that energy is then removed from the system. And so about 23% of the 342 watts per meter squared that the sun shines in every year is actually lost in a process called latent heat. Next, we have about 114% of the 342 watts per meter squared re-emitted by the surface of the Earth. And so the surface of the Earth is actually emitting more energy than the sun is shining onto the Earth in total. And you may think that's funny. You think, well, that doesn't make sense. Well, here's the trick. Only about 12% of that energy gets out. Only about 12% comes out through the atmosphere through atmospheric transmission. About 95% ends up back radiated back down to the Earth's surface for another round. And so even though we are emitting more energy than the sun's putting in, a lot of that gets sent back and goes through another cycle and doesn't get out and escape. About 48% of the 342 watts per meter squared is emitted by the atmosphere, and that heads off forever. And then another 9% or so is emitted by clouds. And if I take all of those brown arrows, all of those things that are emitted by surfaces or atmosphere and clouds, those are what we call long-wave radiation. And you'll notice that long-wave radiation that actually escapes accounts for about 68% of the 342 watts per meter squared. And then when we add that to the stuff that sort of escapes through sensible heat and latent heat, we're at approximately 100%, more or less. So we're basically losing about what we're gaining from the sun. And that means we're in net balance. You know, we get energy in from the sun, we lose energy out through these radiation processes and sensible heat and latent heat, and the net balance ends up zero. It's kind of like your bank account. You put money in, as long as you take out about the same amount, the money that's in your bank account stays constant. The problem occurs when these energy losses don't balance the energy gains. So here's our energy gains, there's our energy losses. When the energy gains exceed the energy losses, that's like putting more money into your bank account than you're taking out and spending. And in that case, your bank account grows. Well, that means that the energy on the Earth grows, and so ultimately that means the Earth heats up. It gets warmer. Opposite scenario, when your energy losses outweigh your energy gains, you're net losing energy to the solar system, and so the Earth gets colder. And you might think, well, what would disturb the balance? What would make it so that you're sort of gaining more heat than you're losing, or vice versa? Well, at least in terms of what humans can do, we end up adding global gases, carbon dioxide, methane, are two big culprits, into the atmosphere. And those actually cause more of the energy to be back radiated to the Earth, and they allow less of that long-wave radiation to escape and head out. And so that throws off the balance, and that means that we end up having more energy gains than energy losses, and as a result, the Earth starts to warm up. And that's where we end up in this system with climate change. That's where we are right now. All right. So that's how the solar radiation impacts the temperatures of the Earth and sort of that balance of energy in and energy out. Another important way that solar energy influences climate is through creation of atmospheric circulation. And so we're going to talk about how that happens and what that means in terms of processes on the Earth. So what I want you to notice in that figure on the bottom, we have pictures of how the solar radiation hits the Earth's surface. And if you look at the poles, the South Pole, the North Pole, what you'll notice is that sunlight takes a much longer path through the atmosphere, and it also spreads out over a larger area when it hits the Earth's surface. That's just because of the way the Earth is shaped. Contrast that to the solar radiation that's hitting at the equator, and you'll notice that it takes a much more direct path, much shorter path, and it strikes the Earth's surface perpendicularly, so it's more focused into a smaller area. Ultimately, what that means is that the solar energy per unit area is actually more at the equator and less at the poles. That in turn means that you get more heating at the equator and you get less heating at the poles. So again, this shouldn't be a shocker. The equator tends to get hotter and the poles are a little bit colder. Why does that matter? Well, that actually drives movement of air masses in very predictable ways. And so the first movement we're going to talk about occurs at the equator in what's called a Hadley cell. In this case, the solar radiation that comes in and hits directly on the equator with that short path really warms up the moist air at the equator. And what happens with hot air? Hot air rises. And so that warm, moist air rises, and it rises up until it hits a warmer layer, that's the stratosphere. And then it stops because it's actually colder than the stratosphere above it. Now, in the process of rising, that's what we call uplift. And as that warm, moist air mass rises, it gets colder and condenses, and that means it can't hold as much moisture. What happens to the moisture? It then comes out as rain. So in these areas of uplift, we tend to get a lot of rain. Once the warm, moist air mass has risen and dumped all of its rain and hit the stratosphere where it can't go any higher, then what it does is it tends to slide along towards the poles. And as it slides towards the poles, it cools a little bit further, and it moves to the point where it hits sort of colder air at more polar regions. And remember, those areas at more polar regions are colder because they're not getting as direct a sun. And so it moves along until it hits a point where it's sort of equal or actually slightly colder and heavier than the air around it. And then because it's slightly colder and heavier, it falls. And in that region where it falls, that's what we call subsidence. All right. Then, once that air mass has fallen, it slides back down to the equator and goes through the whole process again in a big cycle. All right. So to review, we have heating at the equator, and that causes that warm air to rise and cool. The warm air stops rising once it hits the warmer layer of the stratosphere. And then the warm air of the stratosphere flows towards the colder polar regions where it continues to cool. And then once that flowing air is as cold as the more polar air around it, it drops right back down, and then it returns to the equator. All right. At this point, I want to introduce a term, and that's atmospheric pressure. Atmospheric pressure is the force exerted by molecules of air on the other air below it and the surface below. Now, if I think about uplift, that's sort of a rising, that's a lifting off of the air. And so not surprisingly, when you sort of push up, that leads to lower pressure, right? Because you're relieving the pressure because of that lifting up process. Not only do you have low pressure in the areas of uplift, but you also have high precipitation because that warm, moist air is cooling and it can't hold the water anymore, and so you get the precipitation out. Opposite scenario in the areas of subsidence. Here we have the air sinking, so it's sort of like bearing down on the air below it. It's higher pressure, and also because it's already gotten rid of all its water in the uplift zone, once it hits that subsidence and starts falling, it's very, very low precipitation. It's dry. So there's the Hadley cell, and the uplift occurs at the equator, and for complex reasons, the subsidence occurs at about 30 degrees north and also 30 degrees south. All right. Because the uplift is associated with low pressure and high precipitation, and particularly high precipitation, we tend to get rainforests around that uplift zone near the equator. And then we actually get, in those subsidence areas, because it's very dry and high pressure, we actually tend to get deserts. So this is how that climate pattern driven by the solar radiation actually determines the types of vegetations that you can get on a broad scale across the whole surface of the globe. Now we're going to look at the next air pattern, and that's the polar cell. So the polar cell is very similar to the Hadley cell. At around 60 degrees in latitude, north and south, you get again warming of the air at the Earth's surface, and that air rises until it hits the stratosphere. As it rises, not surprisingly, it cools, and then once it hits the stratosphere, and again, that's an area of uplift. Once it hits the stratosphere, it slides along until it reaches the even colder polar areas further north, and also again further south in the southern hemisphere. And then we get again that area subsidence where that moving cold air is actually heavier and colder than the air around it, and it falls down. And then, just like with the Hadley cell, that air at the surface slides back down to where it started, and the whole process repeats in the polar cell. So again, the polar cell is driven by very similar processes to the Hadley cell. The surface air at 60 degrees latitude, both north and south, becomes heated and rises. It cools as it rises, and then it flows towards the pole. Once it's cold enough and dense enough, it falls back to Earth. And then as it hits the ground, it runs back down towards the equator until it reaches sort of that 60-degree latitude and repeats the cycle. Just like at 30 degrees latitude, when you hit that subsidence zone at 90 degrees, right at the top, at the poles, you have high pressure, and you've also lost all your water, and so you have a polar desert. All right, so that's the polar cell. And so there what we have, in red you see the Hadley cells, and in blue you see the polar cells. What you'll notice is there's a missing region in between the two, and that's where the Ferrel cell occurs. Now the Ferrel cell is a little bit different from the Hadley cell and the polar cell. The Ferrel cell is actually driven by the Hadley cell and the polar cell. And so what you'll notice is that where you have subsidence in the Hadley cell, you also have subsidence in the Ferrel cell. And where you have uplift in the polar cell, you also have uplift in the Hadley cell. And that's because that movement down in the Hadley cell drives movement down in the Ferrel cell, and that movement up in the polar cell kind of drives movement up in the Ferrel cell. The Ferrel cell is also driven by exchange of energy between those red tropical air masses in the Hadley cells and those blue cold air masses in the polar cells. And so we have sort of heat flow from the hot air to the cold air. And so we have the hot air there, and we have the cold air up there, and the Ferrel cell sort of moves from the hot to the cold around the cycle. All right, so the region between the Ferrel cell and that polar cell is known as the polar front. So there's our three different types of cells. There actually are 6 cells in general. We have the 2 Hadley cells, the 2 Ferrel cells, and the 2 polar cells. And these ultimately determine what we call climate zones. So if I draw lines at 30 degrees north and 30 degrees south, that's sort of where we have subsidence of the 2 Hadley cells. That borders what we know as the tropical zone. If I then draw lines at the 60 degree north and 60 degree south latitudes, that's where we have uplift of the polar cells. That defines the temperate zone, that's where we live. And then at 90 degrees, that final area is the polar zone. All right. Ultimately, these different zones actually impact the climate in the different regions of the globe. These are sort of broad-scale climate variations. So we said that anywhere you have uplift, you tend to have low pressure and ample precipitation. So that's where the air is rising. So not surprisingly, in those zones of uplift, right around where the Hadley cells are uplifting and where the polar cells are uplifting, you have sort of these areas where it's very wet and it's very low pressure. Opposite scenario where you have subsidence, in these areas you have dry air that's falling, so you have high pressure and very little precipitation. And so that occurs where you have subsidence in the Hadley cells and also where you have subsidence in the polar cells right along the poles. Now you'll notice that I left some white spaces, and that's because so far we've sort of talked about an idealized set of cells where we have the Earth perpendicular. In reality, the Earth is kind of tipped, and so the Earth is closer to the northern hemisphere is closer to the sun in the northern summer, and the southern hemisphere is closer to the sun in the northern winter or the southern summer. So the Earth tilt causes sort of shifts in where the position of these Hadley's, Ferrel, and polar cells are. And so when I have the northern hemisphere tilted towards the sun, it sort of moves everything a little bit up, and so the polar cells move a little bit further north, and it's the warm air moves a little bit further north. And that makes sense because the northern hemisphere is closer to the sun, so the warmth kind of moves up a little bit, and the cold moves up with it all the way from the bottom. What that means is that in the northern summer, that area of uplift due to the Hadley cells is a little bit further north, and so we get wet summers in that first white region. At the same time, that area of subsidence due to the Hadley cell or the Ferrel cell has also moved a little bit north, and so in that second white region, we get a dry summer. On the other hand, when we are in the northern winter, we actually shift the opposite direction. We sort of shift everything down towards the South Pole. And that makes sense because the northern hemisphere is further from the sun and the southern hemisphere is closer to the sun. So again, you take a look at what's happened, and we've actually moved that region of uplift in the Hadley cell a little bit south of the equator, and we've moved the sort of area of subsidence in the Hadley cell also a little bit south, and so we get dry winters in that first white zone, and then we've moved that area of uplift due to the polar cell a little bit further south, and so we get wet winters in that second white region. Very similar story in the southern hemisphere. You can figure it out for yourself. But in that first white region, we get wet summers and dry winters. And in that second white region, we get dry summers and wet winters. All right. That's how atmospheric circulation patterns determine sort of precipitation and pressure zones. They also determine movement of air masses at the Earth's surface, and these are known as prevailing winds. Now, prevailing winds are not like the sort of gusty winds that blow your sailboat on Lake Hartwell. These are large-scale movements of air patterns across the globe. And so the north-south direction of these prevailing winds is actually determined by the flow of the Hadley, Ferrel, and polar cells at the Earth's surface. So if you can figure out how to draw the Hadley cell, the Ferrel cell, and the polar cell, you can actually figure out which way the prevailing winds are going to blow, at least north-south, by looking at the direction of those different cells at the Earth's surface. Don't look at what's going on in the stratosphere. Look at what's going on at the Earth's surface because the prevailing winds flow right along the Earth's surface. So what that means is that because those polar cells flow towards the equator, we have the prevailing winds blowing south at the North Pole and north at the South Pole. The next region, where we have the Ferrel cells, we actually have the air moving north in the northern hemisphere and the air moving south in the southern hemisphere. Finally, in the region where we have the Hadley cells right around the equator, the prevailing winds blow south in the northern hemisphere and north in the southern hemisphere. All right, that's the north-south direction of the prevailing winds. That's the easy part. Now comes the terrible hard part, and that's the east-west direction. So prevailing winds don't just blow north-south, they actually blow also in an east-west direction. To determine that, we have to look at what's known as the Coriolis effect. So the Coriolis effect occurs because the Earth is rotating. We all know that. We all maybe know that the Earth rotates sort of in the direction where if you took Alaska and moved it towards Russia, it kind of goes around in that direction. But here's what happens with the Coriolis effect. It turns out that the Earth is moving faster at the equator than it is at the poles. And that's because it's fatter at the equator. And so if you look at that circle around the equator, it's got a lot more to it than the circles that you can draw at the poles. And so if the Earth spins around in one day everywhere, then it's got to be moving faster in the fat part because it's got to get around a bigger distance than it's moving at the sort of narrow parts of the poles. And so this matters because the winds are sort of moving with the inertia of their starting location. They're maybe not paying attention to the fact that the Earth below them is sort of rotating. What does that mean? And again, this is going to be tricky, so you might have to watch this a couple of times. So if there was no rotation to the Earth, and I had a wind starting, and this is the wind that's associated with the Hadley cell. So this is the wind that's blowing right around the equator. If I have a wind blowing south here, and the Earth wasn't rotating, it would go straight down like that, from the tip of Florida down. Now, on the next slide, I'm going to show you exactly the same animation for that black dot, but I'm actually going to slide the map a little bit to sort of get the Earth to rotate. So again, this can look like an optical illusion, but that black dot is still moving perpendicularly down on the screen. The only difference is the Earth has shifted below it. All right, so that's what would happen without a Coriolis effect. That's what would happen if all the latitudes were rotating at the same speed. But we just said that the closer you are to the equator, the faster you're going because you've got a fatter area to get around in a single day. And so that means that those more southern latitudes, you actually have more rotation than the northern latitudes. And so rather than that black point just sort of moving along that dark blue arrow, you actually have movement along that light blue arrow. So you have this deflection, and the deflection is towards the west. And so in that Hadley cell, the trade winds blow south and they deflect to the west. So at the 30-degree north high pressure zone, you have the winds flowing south and they're deflecting to the west. And these are called trade winds. And I want to point out that in the southern hemisphere, the winds that border the equator are also the ones that are called the trade winds. Okay, so on either side of the equator, you have trade winds. In the southern hemisphere, they're blowing south. In the northern hemisphere, they're blowing south. In the southern hemisphere, they're blowing north. And in the northern hemisphere, they're deflecting to the west. All right, next we're going to look at the flow that's associated with the Ferrel cell. So again, this is flowing north. And if the Earth wasn't moving, we would just have the wind blow straight up like that black dot. Again, I'm going to show you the exact same animation of the black dot, but I'm going to slide the map below to have rotation. So that's what you would have. That's where the winds would end up without any Coriolis effect. That would be if all the different latitudes were rotating at the same rate. That would be the case, for instance, if instead of a globe, we had a cylinder. But that's not the case, right? We already said that the more polar latitudes are rotating more slowly. And so instead of that dark blue arrow, what we actually have is the winds kind of blowing along that light blue arrow. And so that means the winds are deflecting to the east. And so winds flowing north from the 30-degree north high pressure zone actually deflect to the east. And for reasons that are completely unclear, these are called westerlies. So the winds, the prevailing winds that blow east or deflect to the east are called westerlies, and that's true in the southern hemisphere as well. Westerlies deflect east, both in the northern hemisphere and in the southern hemisphere. All right, the final prevailing wind is the one associated with the polar cell. And remember, this, at least in the northern hemisphere, flows south, so we're going to go down like that. And that's how the winds would flow if there was no rotation at all. However, we do have rotation, and so again, that animation is exactly the same. The only difference is the Earth's moving, and that's the blue, dark blue line. Now, that's the case without the Coriolis effect, but remember, the further south or the further closer to the equator you are, the faster the Earth's moving or the faster it's rotating, and so we actually have that. Winds moving along that light blue line, and so again, they're deflecting to the west. And so winds flowing south from the 90-degree north high pressure zone actually deflect west. Again, for reasons that are completely unclear, these winds that deflect west are called easterlies. And again, in the southern hemisphere, the easterlies also deflect west. All right, so those are our prevailing winds. We have the winds blowing north that deflect, the winds from the north blowing south, and those deflect west. We have the winds blowing north that deflect east, and we have the winds, again, those trade winds blowing south that deflect west. So there's your easterlies, your westerlies, and your trade winds. I will leave it to you to try and figure out what's going on in South America and or to look that up in your book. I believe your book goes through that. All right, so again, that's a bit of an idealization because these winds are not just blowing over a sort of homogeneous, bland Earth surface. They're actually blowing over an Earth surface with a lot of structure. And one of the biggest structure is some of that surface is land and some of that surface is water. And water has a higher heat capacity than land. What that means is it takes longer for water to heat up and it takes longer for water to cool down. So far, so good. What that means is that in the summer, the air over the water is cooler and denser, and so it's got higher pressure. And in the winter, it's the air over the land that's cooler and denser and has higher pressure. Why does this matter? Well, this actually changes prevailing winds because winds tend to blow from high pressure zones to low pressure zones. That makes sense. There's a lot of push and pressure in the high pressure zones, and so they get pushed into these lower pressure zones without as much push. So that actually changes exactly how the prevailing winds blow. So you take a look at these figures, and what you'll notice is that they're more or less following what we would expect based on the easterlies, westerlies, and trade winds, but there are some deviations, and those deviations are driven by, to a large extent, that difference between water and land. It also means that we get seasonal shifts in the prevailing winds because we have that change where the cool, dense air is over water in the summer and the cool, dense air is over land in the winter. And so you have sort of that where the high to low pressure flow is actually changing from land to air versus air to land. All right, so that is the prevailing winds. It's the movement of air over the Earth's surface. The prevailing winds are also important because they flow over the ocean surface, and what they cause there are what we call ocean currents. They actually cause these broad-scale movements of ocean water at the surface, and that, again, is important in terms of climate. Now, water does not move sort of exactly with the wind. Water moves at an angle, and again, this is because of the Coriolis effect. And as a result, surface currents are kind of similar to prevailing winds. They kind of mostly go in the same direction, but they're not quite identical. And I don't expect you to know exactly where these flow. I just want you to know that the currents are mostly driven by the prevailing winds. They're similar, but there are differences. And again, that's because of the Coriolis effect. All right. So that's the movement of the surface waters. You have these large-scale currents that kind of run over the oceans all across the globe. But the ocean isn't two-dimensional, it's actually three-dimensional. And so you also have ocean currents that cause movement in the vertical direction from the surface waters down to the lower waters. So overall, your surface waters tend to be warmer and less saline, less salty. And your deep waters tend to be cold and salty. And these two waters actually mix in two types of locations. One is known as downwellings and the other is known as upwellings. So let's take a look at that. Downwellings occur on the coast of Antarctica and Denmark. And in these areas, they're more towards the poles. So this should start to make sense to you. What's happening is that tropical warm water that's been heated by the sun is moving with the prevailing winds, and it's moving to the poles where it's sort of cooling down and losing heat. And eventually it reaches a point where it's cooler and denser, and ice is forming. And so not only is this water cooler and denser, but as the ice forms, it leaves the remaining melted water more salty. And so the freezing increases the salinity of the remaining water. So now you've got this cold, dense, salty water that's actually denser and colder than the water below it, and so it starts to sink. And as it sinks, we sort of get this pushing down, this downwelling, this movement of the surface water down into the depths of the ocean. And so there's an example of where that's happening. You have that flow of the warm water up towards Greenland, and then it sort of moves down into the cold water, and that's the downwelling. All right. Upwellings occur on the western coasts of North and South America, and also in the Pacific Ocean. Now here again, it's the prevailing winds. And the prevailing winds blow parallel to the coasts in these regions, and as a result, they force warm surface waters away from the coasts, and those surface waters that were warm are then replaced by colder water from deeper below. And so that's sort of the movement of water up from below, and this is what's known as an upwelling. And upwellings are particularly important because they bring sort of all that stuff from the bottom back up into the surface waters. And so when things die, they tend to fall, and so they end up on the bottom. But they take with them a lot of good nutrients that living organisms could use. Most living organisms have trouble getting down there, though, because there's no sunlight, and sunlight drives most of life. So you have your phytoplanktons photosynthesizing and your zooplanktons and all that sort of stuff up in that surface water. And so these upwellings actually bring some of those nutrients that were trapped in the dead animals and dead plants back up to the surface for reuse. And so there you see an upwelling where we have this cold blue water come up, and then it sort of rises, and you get that warm water up at the surface. All right. So the different climate zones, the prevailing winds, the ocean currents, all of these are very broad-scale patterns of climate across the globe as a whole. And that matters. That matters as a determinant of climate. But climate is just average weather. And so average weather in a particular location is not just determined by these global processes, it's also determined by more local processes. And so next what we're going to talk about are the regional factors that can influence climate. One of the big ones is proximity to water, and in particularly oceans. Very, very large lakes like the Great Lakes can also matter. So when you are proximate to oceans, or when you're very close to oceans, you end up in what we call a maritime climate. And in these areas, you have smaller variation in daily and seasonal temperatures, and you also have a lot higher humidity, more precipitation. The opposite is the continental climate, where you have much greater variation in daily and seasonal temperatures and lower humidity. And again, that should all make sense given that higher heat capacity of water, where it sort of cools down more slowly and heats up more slowly. So everything's kind of more moderate, close to water, close to oceans. And we can actually see this effect even in South Carolina. So Sullivan's Island is a barrier island off the coast in South Carolina, and it's about 1 hour inland from Sullivan's Island where you get to Somerville, so it's quite a bit more inland. And what you'll notice is that the cold temperatures in Somerville are colder than the cold temperatures in Sullivan's Island. Somerville, on average, gets down to about 34 degrees Fahrenheit, whereas Sullivan's Island, that maritime climate, only hits 37. It's a little bit warmer. At the same time, the high temperatures in the summer on Sullivan's Island are not quite as high as the high temperatures in Somerville. So it gets up to 92 in Somerville, it only gets up to about 91 in Sullivan's. So you have that lower range of temperatures in Sullivan's Island. It goes from 37 to 91 versus that larger range, greater variation in Somerville, where we're going from 34 to 92. All right, so oceans matter. Another thing that matters, also something you can find in South Carolina, is mountains. And mountains are important because they influence all three of those factors that kind of are put together to make up climate. Mountains influence wind, temperature, and precipitation. So I think back in the first lecture, we talked about how temperature decreases as you move up a mountain. We talked about Mount Mitchell and how there's a sign at the bottom of Mount Mitchell that says, take your coat. Because even if you're hot at the bottom of the mountain, it's a lot colder by the time you get to the top. And so temperature decreases as you go to higher elevations. That shouldn't be surprising. If you think about the Rockies, you've got sort of those glaciers on the tops of the mountains, even though it's quite warm below, down in the valleys. Mountains also influence precipitation, and they cause sort of precipitation increases and decreases depending on where you are on the mountain. So as warm, moist air blows up the mountain, because it's colder at the tops of the mountain, that warm, moist air cools. And just like we saw in the Hadley cell and the polar cell where we had those regions of uplift, anytime we have warm, moist air that's forced up, it cools, it condenses, and it forms precipitation. So you get a lot more precipitation on the windward slopes, the slopes where sort of that warm air mass first moves up and deposits all its rain. Now, once it gets to the top of the mountain, it's used up all its rain, and so this is like that area of subsidence in the Hadley cell and the Farrell cell. Again, we're going over to the other side. We've used up all of our our precipitation, all of our moisture. We're cold, we're dense, and now we're going to sort of sink down the other side of the mountain with no moisture left at all, and so we get very low precipitation on the leeward side, and that's what's known as a rain shadow effect. All right, mountains also influence wind speed, and so this is sort of driven by daily temperatures. And so anytime you have an east-facing slope, it's warmed by the morning sunlight. It's because the sun rises in the east. And this warming of the air on the east slope can actually cause upslope winds that sort of blow up the mountain in the morning or early afternoon. By the time you get to the nighttime, you get cooling because the sun's gone away. It's no longer heating the surface. And this cooling is actually more pronounced at high elevations. And that's because you have thinner atmospheres up there. And so there's not as much to trap the heat in. And so you have this much colder, more dense air at the top of the mountains, and that sinks and that causes airflow down the slopes, and that's what we call cold air drainage. All right. So oceans matter, mountains matter. The other thing that influences regional or local climate is vegetation. And generally vegetation does this by altering energy exchange. And there's sort of two ways in which vegetation can alter energy exchange. One way is by affecting what we call albedo. Albedo is the amount of solar radiation that a surface reflects. And if you've ever walked on sort of dark black sand, lava sand beaches, they're very, very, very hot. You contrast that to white sand beaches, and they can be hot, but they don't get quite as hot. And that's because dark colors absorb radiation better than light colors. And so if you have a dark vegetation type, something like a dark conifer forest, it actually has lower albedo. It's absorbing more radiation and reflecting less radiation than a lighter surface, something like a grassland where you have a higher albedo and more of that solar energy gets reflected. Shouldn't be really surprising then that at your higher elevations and at your higher latitudes where you have sort of colder temperatures and less solar radiation, you tend to get these dark conifer forests. They're trying to capture as much light as they can, as much solar radiation as they can. You tend to get lighter vegetation in areas where you get more solar radiation in general. All right. The other way that vegetation can alter energy exchange is through changes to the surface texture. So if I have a very rough surface of mixed trees, that actually allows greater transfer of energy between the sort of surface and the atmosphere. Contrast that to a smoother surface, something like a grassland, and we have less transfer. And that's just because the air moves faster over that smooth surface, so there's less opportunity for heat and transfer of energy versus the rough surface where the air gets trapped and there's sort of just more time for the heat exchange to occur. All right, so now we've talked about these global factors that influence climate and the local factors that influence climate, the regional factors. The other place, so it's not just over space that we see climate vary, we also see climate vary over time. We see temporal variation in climate. And this actually results from the tilt of the Earth's axis. So again, we were talking about how those different atmospheric circulation cells change going from summer to winter. That was because the Earth was tilted. And so the northern hemisphere is closer to the sun in the northern summer, in our summer, and the southern hemisphere is tilted closer to the sun in the southern summer, which is actually our winter. What this means is that we have large changes in temperature in the temperate zones. And we know this, right? We know that it's a lot warmer in South Carolina in the summer, and that's when we're tilted closer to the sun. And it's a lot colder in South Carolina in the winter in December, and that's when we're further from the sun just because of that tilt of the Earth's axis. In tropical zones, we don't tend to get much change in temperature over the season. And that's because, it doesn't really matter whether the top's tilted towards the sun or the bottom's tilted towards the sun. Right around that middle, you're always about the same distance from the sun, right? And that's the equator. What we do see, though, in the tropical zones is seasonal variation in the amount of precipitation. And that's because of movement of what's known as the intertropical convergence zone. So this is a zone of maximum uplift, where the sort of maximum warming and lifting of the air up, and that corresponds to exactly where the sun strikes the Earth most directly. And so this actually moves from 23.5 degrees north in June to 23.5 degrees south in December. And so that alters exactly where you get the most precipitation. And so you get these seasonal patterns, rainy, wet seasons, and more dry seasons around the equator. All right, so seasonality matters on these broad scales, looking at sort of winter and summer in the northern and southern hemispheres, and sort of these rainy and dry seasons around the equator. But it also matters on a more local level, at least in particularly in temperate regions, where we have that variation in temperature over the season. One area where seasonal variation is very important is in aquatic environments. And in these environments, you actually get sort of movement of water in response to seasonal climate variation. So I'm first going to talk about movement of water that occurs in the fall or in the autumn. And this occurs due to sort of stratification of the different water layers in a lake. So the first layer that we have is what's known as the epilimnion. And this is that warm surface layer where the sunlight sort of can penetrate through. And because the sunlight penetrates through that warm area, it warms it up, and we also have active phytoplankton that can photosynthesize, and zooplankton sort of living in that zone. The next zone down is what's called the thermocline, and this is a zone of rapid temperature decline. The sun's not really penetrating in there as much or at all, and so you get this sort of rapid fall off in temperature because it's not being warmed up. The third level is the hypolimnion, and this is a stable layer of the densest, coldest water. All right, so lake turnover occurs as those surface waters in temperate regions cool down because the Earth is no longer tilted, or the northern hemisphere, for example, is no longer tilted toward the sun. We're moving out of the summer and into the winter, and so that surface water cools down as the air temperatures cool down. As the surface water cools down, it becomes colder, it becomes more dense, and ultimately it becomes colder and more dense than the water below it, and that causes it to sink. As it sinks, and this is partly aided by wind, the underlying water below ends up being pulled up, and it moves to the top. And so you get this turnover in the water where the surface water moves down and the lower water moves back up to the surface. So that occurs in the autumn. A related but slightly different process occurs in the spring. In this case, through the winter, we have a layer of ice on the water, and ice is less dense than water. That's just how water is. When it freezes, it becomes less dense just because of its structure. However, as the ice melts, it leaves a layer of very, very cold water and actually some of the densest water at the surface of the lake. And so this really dense layer of cold water is actually denser and colder than the water below it, and it begins to sink. Once again, as that water sinks, aided by the wind, the stuff that replaces it is the water from the bottom of the lake, and so we get this cycle or cyclic movement where the surface water goes down and the bottom water, the lower depth water, comes up to the surface. So this occurs both in the fall and in the spring, and it's important for a couple of reasons. First, just like in the oceans, just like with the currents, when organisms die, they tend to fall to deeper, lower water. And so they take all those good nutrients with them. And just as the upwellings bring the nutrients from the bottom of the ocean up to the surface waters where there's a lot of active light and the sun can penetrate, same thing happens in lakes. These turnovers actually bring those nutrients back up to the top of the lake where they can be used in that very living layer of the lake. The other thing that happens is that the turnover brings oxygen back down to the bottom of the lake. Oxygen can kind of only get in from the atmosphere, and so it tends to be more concentrated in the surface waters, and during this process of turnover, the oxygen gets dragged down with that surface water into the bottom of the lake. All right. So that's seasonal variation, and that's sort of a shorter term variation. It takes place over a year. We also have longer term climate variations, and sort of on an intermediate time scale, we have a couple of processes. One is El Niño, Southern Oscillation, and in our region, this tends to cause increased precipitation, but it also has effects around the globe. When we have El Niño years, we tend to have dry conditions in Southeast Asia and Australia, and then after El Niño, we tend to get what's known as a La Niño period, and that causes an increased risk of droughts and fire. Another sort of cyclic process that's longer than a year is what's known as the North Atlantic Oscillation. And these affect Europe, Northern Asia, and the east coast of North America. And again, these are sort of multi-year cyclical changes in climate, in both precipitation regimes and temperature regimes. Oops. Finally, we have the Pacific Decadal Oscillation. Not surprisingly, this occurs on about the scale of 10 years. And this affects northwestern North America and Central America, Asia, and Australia. And again, these are sort of intermediate timescale climate variations. If we look at really long timescale climate variation, one of the big ones is what's known as the Milankovitch cycles. And these are regular changes in the tilt of the Earth's axis. Remember, we get our summer and our winter because the Earth is tilted, and so as it moves around the sun, sometimes the northern hemisphere is closer and sometimes the southern hemisphere is closer. Well, it turns out that there are regular changes in the tilt of that axis. There's also regular changes in the shape of the orbit that the Earth takes as it moves around the sun. And finally, there's regular changes in the Earth's orientation relative to other celestial bodies, relative to other planets and moons and that sort of stuff. And so ultimately, this determines what's known as Milankovitch cycles, because Milankovitch was the one who figured out that these long time scale, many thousands of years time scale variations correlate with glacial and interglacial periods. So you can relate when the glaciers sort of move in to what's going on in the celestial system with the tilt of the Earth's axis, the shape of its orbit, and where it is relative to all the other bodies out in space. All right, so that's climate. That's sort of all the different elements and factors affecting climate. But like I said, the physical environment also includes another sort of facet, and that's the chemical environment. And so back when I was just talking about climate, I sort of simplified the story. I showed you that paper where scientists were trying to predict where different Australian plants could grow, and I showed you the climate figure where they could kind of do a good job just by using 5 climate variables alone. Well, it turns out they actually looked a little bit more, and they actually looked at the chemical environment as well. And so they looked at sort of soil features and used those to try and predict where you would find plants. And they did quite well with that as well. And then when they combined soil and climate, they actually did very well at predicting exactly where the plants would be found. And so what that means is that the climate matters in terms of species distributions, but sort of the chemicals, the nutrients, the gases, the pH, the salinity, all of that matters as well in determining where you can find different organisms, and then what that means is where you can find different ecosystems and sort of basically all of ecology. So again, don't forget the chemical environment, it matters as well. There's a lot of different chemicals out there, they all kind of matter. We're going to just focus on a few. So the first one we're going to focus on is salinity, and this is the concentration of dissolved salts. This includes table salt, sodium chloride, but it also includes a lot of those other salts that you learn about in freshman chemistry. Your magnesium salts, your calcium salts, sulfates, bicarbonates, potassium. These salts come from a number of different sources. One big source is from gases that were emitted by volcanoes in early history. This contributed to some of the elements and some of the salts that are out there in our different soils, in our different bedrock, and in our waters. We also have salts added through the breakdown of minerals and rocks in the Earth's crust. And again, these get sort of added to the soils and then washed into the waters. And so they determine the salinity and the concentrations of the different salts in the different regions. And so oceans are quite salty. They're in general 33 to 37 parts per thousand salt. And actually, the saltiest areas are near the equator, and the least saline oceans are actually at the higher latitudes towards the poles. We also have variation in salinity in different soils. Not surprisingly, soils that are close to oceans tend to be more salty than other soils. So things like salt marshes tend to be particularly salty soils, and that really restricts the plants that can live there. Another area where you get high salinity soils is in arid regions, and that's because water brings all the salt with it, but then as it evaporates into the atmosphere and floats away, the salt doesn't come with it. Just the water evaporates and it leaves the salt on the surface. And so you can actually go to some deserts. There's a number out in Utah and in the California deserts, especially in around Death Valley, where you have what's known as salt flats. And they actually have race car drivers driving on these salt flats. And they're really interesting environment, really kind of neat areas where you actually see crystals of salt all over the soil surface. Salinity matters because it affects the ability of different organisms to absorb water. Hopefully you saw that in chemistry, where we have sort of a hypotonic solution. And in that case, the sort of environment around the cell has less salt, and so water flows into the salty cell. That can cause the cell to explode. We have an isotonic solution where you have no real net gain or loss of water, and then we have a hypertonic solution where there's more salt in the surrounding environment than in the cell itself, and so water flows out. So again, salinity affects the ability of organisms to absorb water. Some salts are also nutrients. So, you need potassium, you need magnesium, you need calcium. And a lot of plants and animals need these different nutrients, and so the availability of these nutrients is sometimes determined by the salinity. And so that's sort of two ways in which salinity can affect who grows where, who can tolerate different hypotonic or hypertonic environments, and who needs what particular nutrients at what concentrations. So again, I said arid environments tend to be some of your saltier, and one of the reasons is because of this process known as salinization, where you get progressive buildup of salts at the soil surface. And again, this is actually a picture of Death Valley. This is, I believe, something like Devil's Golf Course, something like that. And here we've had a process where the water has moved this salty water has moved to the surface, the water's evaporated, and left this really thick crust of salt all over the ground. Not surprisingly, a lot of plants have trouble growing in this stuff, so it's a quite desolate area. So that's salt. I said the next one we're going to talk about is acidity. And acidity measures the ability of a solution to behave as an acid or give up protons. And the opposite is alkalinity, which measures the ability of a solution to behave as a base or accept protons. We typically measure measure acidity as pH. You can do that with a pH meter, with litmus paper if you're old school. And changes in pH are important because they actually directly affect metabolic activity. They affect sort of the living processes of the cells. pH is also important because it can affect the availability of nutrients. If you have certain chemical compounds protonated versus not protonated, then they may be harder or easier for cells to transport and take up and use for whatever they need those particular chemicals for. Not surprisingly then, a lot of organisms tolerate very limited ranges of pH. And so if you take organisms that are used to growing in acid soils and you move them to more basic soils, they tend to not do very well. Same thing if you take organisms that are good at growing in basic soils and move them to more acid soils, they typically die. Different underlying bedrocks are one reason why you get different acidities in the soil. So granite bedrocks tend to have more acid soils than limestone. But it's not just that underlying base material. You also sort of have other factors that impact soil acidity. And so basic salts tend to leach away faster. They kind of flow with the water more. And so in general, soils tend to become more acidic as they age. So that's acidity. The final chemical environment that we're going to talk about, again, there's a lot of other chemicals out there that do matter, but the final one we're going to talk about is oxygen. And that's a gas. And so oxygen becomes a problem typically when it's low availability, and that's what we call a hypoxic environment. Ironically enough, though, initially oxygen was absent from the Earth's surface, and it was actually toxic to most early life. And in fact, it's still toxic to certain organisms. Certain anaerobic bacteria, for instance, are killed on contact with oxygen. But most organisms around today actually require oxygen to carry out metabolic processes, to carry out aerobic respiration. And one of the reasons that a lot of organisms have evolved to use oxygen is because the concentrations of oxygen in the atmosphere have been stable for about 65 million years. It's a really good, sort of stable, reliable thing to depend on. It's not surprising that evolution has tuned systems to use it. So typically terrestrial systems are not super limited by oxygen, right? We don't have a huge problem getting oxygen to breathe. That may change as we cut down all our forests and climate change, but historically that's not been a problem. Where oxygen becomes a problem is in aquatic systems. And so generally oxygen gets into aquatic systems by diffusing into the water, and so it sort of diffuses into that surface layer. So anywhere you have waves or currents or sort of turnover, for instance, in lakes, you actually expose more surface area to the atmosphere and you can get more oxygen in. Contrast that to very stagnant water, maybe in bays or in sort of some freshwater ponds where not much is moving, or even some soil environments where everything's kind of static and you don't get a lot of oxygen in. That's where you tend to get these hypoxic environments. And so frequently you'll get fish die-offs in bays or in sort of stagnant ponds because they run out of oxygen, because you don't have enough diffusion of oxygen into the water to keep these organisms alive. And so basically you get sort of the highest amount of oxygen in these fast-moving waters where you get a lot of surface exposed to the atmosphere and you get a lot of diffusion of oxygen in. All right, so that's a very brief summary of climate, a very even briefer summary of the chemical environment, and put together those two make up the physical environment that sort of forms the stage on which all of ecology happens. So again, if you have any questions about this lecture or other lectures, email me at sbewick@clemson.edu and I'd be happy to talk.